Time travel to the past is possible if the universe is rotating. Wait, what? Both parts of the statement might seem strange, because according to our modern understanding, the universe does not seem to be rotating, although we can't say that with 100% certainty. And time travel to the past is associated with a lot of paradoxes, and it's not even certain that it's actually possible. But let's not get ahead of ourselves. It seems like no matter where you look, everything in the universe is rotating and moving in orbits around something. The Earth rotates around its axis, stars rotate around their axes, plus they move around the center of the galaxy, which means that the galaxy itself is rotating. If we continue with this logic, we can end up at the scale of the entire universe and ask the question, does the universe rotate? And that's not a simple question to answer. How can the universe itself rotate? How does something seemingly infinite rotate? Can it even spin in principle, and what do modern observational data tell us about this? What are the largest structures in the universe that definitely rotate, and why might a rotating universe allow for time travel to the past? Today we'll talk about all this and more. I'm Andrei, and this is Cosmos Elementary. Besides all the time travel paradoxes, what is so strange in the possibility of the rotating universe? Well, it would be a big problem for modern physics and cosmology. The current cosmological model, which we use to describe the universe, includes two important properties. Homogeneity, meaning the uniformity of the universe everywhere on the largest scales, and isotropy, meaning the absence of a preferred direction in the universe. No matter which direction we look, it should look the same everywhere. And this should be true for any point of observation. If the universe were rotating, it would no longer appear isotropic. So, if we suddenly discovered that the universe is rotating, our modern understanding would go straight out of the window, or at the very least require a serious revision. In October 19, 1946, a brief letter titled "Rotating Universe?" by George Gamow was published in Nature. The motivation behind this letter is similar to the one I mentioned in the beginning. He suggested that everything we see to some extent rotates, including galaxies. Given this, it is possible that all the matter in the universe is in a state of overall rotation around some center that, for example, might lie beyond the regions accessible to telescopes of that time. He even suggested that with tools available at the time, it might be possible to attempt to detect this rotation by measuring the velocities of galaxies. In conclusion, Gamow wrote that perhaps such a rotating universe could be described within the framework of general relativity using a set of special solutions. And indeed, such solutions were found just 3 years later, and with them, the possibility of time travel emerged. But we'll get back to that a bit later. For now, let's try to take a naive look at the question of rotation. At first glance, the sequence from Earth to star to galaxy, then to a cluster of galaxies, and finally to the universe seems logical. But planets and stars are distinct objects that can rotate around their axes. Galaxies, although not separate objects, are still systems of gravitationally bound objects which can also have some common axis of rotation. But the universe? When we ask whether the universe is rotating, what exactly do we mean by that? Are we talking about just all the matter in the universe, or the rotation of space-time itself, like in the case of the expansion of the universe, where it's not that just galaxies are flying away from each other, but rather the fabric of space-time itself is stretching, right? Furthermore, although we don't know this with 100% certainty, it's quite likely that the universe is infinite. And anything related to infinity is always difficult to grasp, and the story with rotation is no exception. It's easy to imagine how an object of a finite size rotates, but how can something infinite rotate? If the universe is infinite, it has no center. So how could it have a single distinct axis around which everything rotates? Mind blown. But here we have some options. As I already said, we're still not 100% sure that the universe is ultimately infinite. Some of you might recall that today three main possibilities for the geometry of the universe are being considered: closed, open, and flat. Yes, so far all measurements indicate that our universe is flat, and most likely infinite. However, it cannot be completely ruled out that it has a closed geometry, meaning it loops back on itself. In that case, the universe would be infinite, even though it has no boundaries, just like the surface of a sphere has no edges. Except here, we're talking about three-dimensional space. This is also not easy to grasp, but two-dimensional analogies help us a little. Now, the rotation of a closed, finite universe is a more intuitive and less mind-bending case. If we return to the idea of an infinite universe, there may not be a single universal rotation. Instead, rotation could be local at certain scales, complex and not limited to just one axis, but involving multiple axes. Here's what else might be unclear. We want to know if the universe is rotating. But if the universe is everything there is, then relative to what is it rotating? Being on Earth, we can easily understand that our planet is rotating by observing the sky. But what can we look at to determine whether the universe itself is rotating? Here people sometimes mention Newton's bucket. It is a thought experiment proposed by Isaac Newton. This is not about specifically whether the universe is rotating, but rather about absolute and relative motion and rotation, as well as absolute space. However, there is a certain connection here. The experiment involves suspending a bucket half filled with water on a rope, twisting the rope along with the bucket until it's fully wound, then releasing it, allowing the bucket to spin. Several stages can be identified here. Before we release the bucket, neither the bucket nor the water is rotating, and the surface of the water is flat. When we release the bucket, it starts to rotate, while the water remains flat for a while. As the water begins to rotate along with the bucket, it does so slowly at first. Gradually, the surface of the water stops being flat, and at the edges the water rises along the walls, causing the surface to take a concave shape. At some point, the rotation speed of the water and the bucket equalizes, and it seems that relative to the bucket, the water is no longer rotating. However, the surface of the water remains concave. If someone were living on the surface of the bucket, they could tell that the bucket is rotating by looking out of it at the surrounding world, just like we do by observing the sky. However, if the bucket were rotating in empty space, with no visual reference points, this person could still understand that the bucket is rotating by the concave surface of the water. We in our universe are unable to look out beyond its limits, but perhaps by analogy with the concave surface of the water, there are certain signs that could help us understand whether our universe is rotating. Why does everything rotate? In our solar system, most planets rotate and orbit the Sun in the same direction. The conservation of angular momentum is one of the key factors here. Let me remind you that a star, along with its system of planets and smaller bodies, forms during the collapse of a fragment of a molecular cloud made of gas and dust. Particles in that cloud are moving in different directions, but still, for example, due to some external influences, the movement of particles is not entirely random, and this cloud has a preferred direction of rotation, even though this rotation is very weak. Next, due to some instability or external influence, the cloud collapses. And what happens to a rotating object when it decreases in size? Here we usually recall the well-known example with figure skaters. When they bring their arms in, the rotation speeds up. The same happens with the material in a molecular cloud, which compresses under the influence of gravity. Due to the conservation of angular momentum, the resulting objects, stars and planets, rotate much faster. But this is the scale of planets and stars. On larger scales, such as galaxies and galaxy clusters, and beyond, it's a bit more complicated, because here the expansion of the universe also comes into play. I have talked about early stages of the universe, inflation, and the Big Bang in my previous videos, like this one and this one. It is currently believed that the structure in the universe exists because at the very early stages, quantum fluctuations were stretched out as a result of inflation, a brief period during which the universe expanded by an enormous amount. These stretched fluctuations created small irregularities in the distribution of matter in the universe. Some areas were slightly denser than others, and this ultimately led to the formation of stars, galaxies, and everything else under the influence of gravity. In addition to the irregularities, there was also small initial motion and angular momentum. That is, just as there was some amount of angular momentum in the cloud that became the solar system, there was also a bit of angular momentum on larger scales. But the difference is that a small cloud collapsed, and this intensified the rotation of the object or system, which became more compact. But on a large scale, the universe was expanding, and here the effect is exactly the opposite. The initial angular momentum as the universe expands kind of dilutes, and the effect weakens. This is in the reference to the rotation of the entire universe. If we are talking specifically about matter, the angular momentum that existed due to the initial irregularities gets spread out due to the expansion, which makes the likelihood of the entire universe rotating much lower. But still, on some scales, it can be preserved and does remain. And once again, these initial irregularities help us out. Although space-time is expanding, the irregularities in gravity allowed galaxies to form. And in certain scales, the distribution of matter became more compact, and the conservation of angular momentum allowed galaxies to rotate. Another factor at play is tidal forces and acceleration. The gravitational attraction between objects such as galaxies that are relatively close to each other exert an uneven effect, and this also contributes to their rotation. In the end, we know for sure that galaxies rotate, as in certain cases we can directly measure the velocities of stars. On larger scales, determining this becomes much more difficult, but it's not impossible. For example, a study in which scientists measured the speeds of galaxies was able to detect rotation in many galaxy clusters. The rotation of an entire galaxy cluster can be caused by the remnants of the initial angular momentum of a protocluster, the uneven influx of matter into it, and mergers with other clusters. But we can go even further. On larger scales, the universe looks like a web, and the threads of this web are made up of galaxy clusters. A few years ago, a paper was published in Nature Astronomy, and in this study there was a mention of the possible detection of rotation in galactic filaments. Scientists used data from 200,000 galaxies, and measurements of redshift indicated that the filaments might be rotating around an axis. On such scale, explaining rotation becomes much more difficult, but still, these are the largest known structures in the universe that could possess rotation. However, even though galactic filaments are incredibly vast, they are far from the entire universe. From what we have learned so far, we can conclude that the larger the scale, the more difficult it is to induce rotation, especially considering the expansion of the universe. Moreover, as I've already mentioned, according to the current cosmological model, it shouldn't rotate, because isotropy. But while the homogeneity and isotropy of the universe are integral parts of the modern cosmological model, originally they were just assumptions. So we didn't know for sure whether it was like that or not, and assumed it to be so. Since then, many different observations have mostly confirmed this, but still, what if we're making a mistake somewhere? What if we're overlooking something? We know that the universe is expanding, and we understand this because we see that the farther a galaxy is from us, the faster it is moving away. But when we say we see, we mean that we measure the redshift of these galaxies. The light waves from an object moving away from us stretches out, shifting to the red part of the spectrum. Thanks to this effect, we know that the universe is not static. But is it possible to determine in a similar way whether it is rotating? Astrophysicist and science communicator Ethan Siegel, in his article, writes that by analogy with how we observe the movement of galaxies along the line of sight from the observer, we can attempt to measure the transverse motion of distant galaxies. If we were to notice a trend in the movement of distant galaxies in one direction relative to us on Earth, it could suggest a global rotation. Thing is, measuring this is not so simple. Given the vast distances in the universe, even if a distant galaxy were moving very quickly, measuring its position change would be difficult. For example, here is a photograph of the Andromeda Galaxy taken in 1888. I tried overlaying it with a photograph of Andromeda taken in 2010, maintaining their orientation and scales. And here's what came out. When you quickly switch between them, it becomes especially clear that over 120 years, the galaxy hasn't noticeably changed its position relative to the stars in our sky. And this is our galactic neighbor. And for galaxies that are billions of light years away, it's even more difficult, many of which we see, if not as points, then as small blurry blobs. In general, trying to determine if the universe is rotating in such a way doesn't seem like a very viable option. By the way, it's not even necessary to observe galaxies. After all, we have the cosmic microwave background radiation, the oldest light in the universe that we can observe, which began freely traveling through the universe just 380,000 years after what we refer to as the birth of the universe. It is the cosmic microwave background radiation, and I've also talked a lot about this and made separate videos on this topic. This first light of the universe plays a very important role in modern cosmology. It serves as one of the key pieces of evidence for the Big Bang and tells us a lot about the properties of the universe. We are located at the center, not of the entire universe, but of the observable universe, and at the center of a kind of a bubble, the surface of which is where the cosmic microwave background radiation reaches us from. This is also referred to as the surface of last scattering. If the universe were rotating, looking at different regions of the cosmic microwave background on the sky, we would see different patterns. In other words, we would observe anisotropy. But the thing is that the cosmic microwave background is actually very homogeneous, only with very tiny temperature fluctuations. If we don't take into account very small fractions of a degree, it can be shown as a sky map filled with a single color, representing the same temperature everywhere. But still, there are some anomalies in the CMB. However, this doesn't necessarily mean that these anomalies are caused by the properties of the universe itself. It's quite possible that these are more related to the issues with our observations. A prime example is the famous Dipole anisotropy. Here is a map of the cosmic microwave background showing this anomaly. It demonstrates that one half of the sky is slightly colder than the other. The difference is very small, just a few millikelvins, but it is measurable. So could this be a sign of anisotropy, of some kind of preferred direction, the evidence that the universe is indeed rotating? Well, unfortunately no. This anomaly occurs solely due to the motion of our solar system relative to the microwave background, leading to a small Doppler effect. Radiation in one part of the sky shifts slightly to the red part of the spectrum, while in the opposite direction it shifts towards the blue. But there are more subtle anomalies in the CMB, such as the so-called axis of evil. I made a separate video about it. However, despite the presence of some anomalies, there is still no convincing evidence that the cosmic microwave background is truly anisotropic, or that the universe might be rotating. There have been special studies that used various models, and so far, no conclusive signs of anisotropy in the CMB have been found. But there are other methods, for example, the direction of rotation of spiral galaxies. Here's the idea. Spiral galaxies can rotate in either direction. In an isotropic universe, the direction of rotation should be distributed randomly, and no matter which part of the sky we look at, the ratio should be around 50-50. But in this paper, based on a sample of tens of thousands of galaxies, a slight deviation of a couple of percent was found. A small bias, but it could indicate some anisotropy and the presence of a preferred direction in the universe. However, again, the issue might simply lie in the study itself. rather than in the universe. Very recently, there was another study from the same author based on James Webb Telescope data. It showed a much stronger bias, with 2/3 of galaxies from the sample having the same direction of rotation. But in this case, the sample was much smaller, only 263 galaxies, against tens of thousands in previous studies. So it needs further investigation. Since we're talking about wild ideas, here's another one to consider. You might have heard of the idea that the entire universe could exist inside black holes. There are some parallels, like how the observable universe has a horizon, and so do black holes and all that. But in practice, we don't have any serious reasons to believe that this is actually the case, although there is a small number of supporters of this idea among scientists. On the other hand, in such situation, it would be easier for us to imagine how the universe could rotate. After all, black holes should rotate. It's one of their few properties. If there is an entire universe inside a rotating black hole, then there you have a rotating universe, easy. And you don't have to rack your brain trying to imagine all of this. Well, almost. By the way, black holes like to mess with time. So now let's talk about how the rotation of the universe is connected to time travel. At the beginning of the video, I mentioned a letter by George Gamow, where he speculated about the rotation of the universe. But these were just speculations. He did not present a concrete model. But just 3 years later, the mathematician and logician Kurt Godel presented such a model, which he described in this paper. Interestingly, he didn't just come up with some version of a rotating universe. He described it using the language of general relativity. In other words, he found exact solutions to Einstein's equations that described such a universe. This universe has at least one of the key properties of our universe, homogeneity. That is, it's the same everywhere. And also, it's infinite. Beyond that, similarities end. Godel's universe has a negative cosmological constant. It does not expand, meaning it's static, and what prevents it from collapsing is the rotation. Rotation is indeed very counterintuitive. At first, we tried to imagine where the axis of rotation would be in the universe. There isn't a single axis here. Every observer in such a universe would see themselves as the center of rotation. The farther an object is from the observer, the stronger the rotation. This is similar to how we perceive ourselves at the center of the expansion of our universe, as shown in these examples. No matter which point we choose, it will seem to the observer that they are at the center. The thing is, visualizing or imagining a rotation like this becomes quite problematic, but in the language of mathematics, it can be described. Another important point we touched on earlier is that it's not just matter that's rotating here, but space-time itself. And from this it follows that the trajectories of light are governed by the curvature of space-time. In our universe we observe this, for example, in the effects of gravitational lensing. In a rotating universe, light would also follow this rotation, meaning that emitted light would eventually return to the same point from which it was emitted. This means that potentially one could see images of their own past. In such a universe, there is a limit to how far one can look, and there exists what is called an optical horizon, beyond which it is impossible to peer. While researching for this video, I found an entire scientific paper dedicated to visualizations of Godel's universe. What an observer would see in such a universe. It includes both images and animations. I'll leave a link in the description so you can check out everything that's there. But now, here's the strangest part. The behavior applies not only to light, but to everything in general. Godel's universe implies the existence of so-called closed time-like curves. Essentially, Godel was one of the first to discuss the existence of such things within the framework of general relativity. These are word lines, meaning the paths of particles or objects in both space and time, which bring their object back to its starting point. Again, this applies to both space and time. In normal conditions, If we orbit around the Earth and return to the starting point, we would simply return to the same place on Earth. But time would move forward. So by moving along a closed time-like curve, you would not only return to the starting point in space, but also to the exact moment of departure. In Godel's universe, these closed time-like curves exist. And in theory, if you boarded a spacecraft, you could return to your own past. But then, all the familiar problems arise, like violations of the principle of causality, grandfather paradox, and all the rest. And well, that's a problem. But Godel's model does not describe our universe. It is artificial. Moreover, observations show that our universe differs from what is described in this model. At the very least, it is expanding. And as we've already established, there are no signs of rotation either. Godel's motivation for creating this model was in part to demonstrate the incompleteness of general relativity. However, Godel's work motivated further research into this issue. And today there are both more complex models of rotating universes and other types of closed time-like curves, which I may cover in future videos. In any case, at least in theory, general relativity does not forbid time travel to the past. As far as we can say, our universe, one way or another, on a global or local scale, is not rotating. However, we cannot completely rule out this possibility. But if convincing observations in favor of universal rotation were to appear, we would have to seriously reconsider our understanding of our universe. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, leave a like, comment, and subscribe for more videos in future.